references. Okay, so let me acknowledge my collaborators. The work is done by 2 master students, and one of the tilted 101 field is in collaboration with Peter Holdsworth. So let me start with the introduction. So spin ice is a class of materials. Basically, the magnetic moments lives on a pi core. So basically, it's a corner-sharing tetrahedron, and these are the most famous dipolar spin ice materials: holmium titanate and dysprosium titanate. And the holmium and dysprosium ions are the magnetic ions. And in this systems, these rare magnetic ions has a large moment. So in this case, they have the moment is like 10 Bohr megatons. It's huge. And this particle lattice, these moments live on this particle lattice, and this is a class of materials which has this geometrical frustration. So the previous speaker already mentioned something about frustration. So in this case, the frustration is actually coming from the geometry of the lattice. So think of that you have Ising spins on a triangle, and if you put antiferromagnetic bonds on each link, and there's no way that you can classically satisfy all the bonds. For example, if you put the bonds, the spins in this fashion, this bond will be unhappy. And but you flip the spin, this bond will be unhappy. So the best you can do is to make the pairs equally unhappy, and this equally unhappy produces some degeneracy. And you can start from this simplex and build up some very, very complicated lattice structures. And the material scientists they actually build all of this materials, and you can have a very complicated lattices. And so all these materials they share some features. So because of this degeneracy, so there's a large number of degenerate classical ground state. So if you have any small perturbation being quantum or classical, it's going to give you to a very novel ground states. So what we're interested in is in these spin ice materials. Okay? So the way to define so these materials they have the spins are Ising spins. But how do you define Ising spins on a tetrahedron? Okay? How do you define up and down? So the way these spins are, these systems, the spins, there's a single ion and anisotropy, and this anisotropy actually is along the 111 direction of this of the lattice. So the spin will either point into the center of the tetrahedron or point out of the center of the tetrahedron. So that defines your Ising variable, in or out. Okay? So why is this called? So this is because there's the crystal field of this holmium ion in this environment. Actually, the ground state is a Ising doublet, and the first excited state is about 200 Kelvin. So in the temperature region of interest, basically it's a Ising. You can consider the spins as Ising doublets, okay, as Ising spins. And this configuration, okay, if you put to minimize the single tetrahedron, you can follow the exercise as proposed by the previous speaker, that you try to sum up the single tetrahedron, the total, the vector sum of the spins in single tetrahedron to be 0. But now your spins is confined in the 111 direction. So the only way you can do this is you have 2 spins pointing in and 2 spins pointing out. So for this for this tetrahedron, you have a 6-fold degeneracy. And if you put this in a lattice, then you have extensive number of degenerate ground states. Okay? And that actually is equivalent to water ice. So water, H2O, you have an oxygen ion at the center of the tetrahedron, and you have 2 protons closer to the oxygen ion and 2 protons further away from the oxygen ion. So you can consider this just if you draw an arrow here, it's mapped directly to a spin ice. Okay, and not only this. Not only this, so Pauling in 1935 estimated this is residual entropy of this water ice, and people did the experiments and the measurement. Okay, so this is the rough estimate you can do, and this is the number of degenerate ground states you have. And if you take this number, take a log, and divide by n, you get this entropy. And so here is the measurement data in this dysprosium titanate. And if you integrate below this area, integrate the area below the curve, okay. So you start from 0 and it goes to this number. And at high temperature, your entropy should be R log 2, okay, because you have 2 degrees of freedom. And so, but you're missing this part of the entropy, and this missing part of the entropy is actually this number. Okay. And what's shown here, the squares are the experimental data, and these are the molecular simulation data. Okay. And so you see that experiments does measure this finite residual entropy. Okay. But there's one problem. So all this argument, okay, all this argument, we just consider nearest neighbor interactions. So to minimize this interaction in a single tetrahedron, we consider that the system has to be in the ice state. But in all these materials, they have large moments, and these large moments give rise to dipole interaction. So it seems that we're using the wrong model to get the correct physics. Okay. So people use this full dipolar spin ice model and did a simulation, and indeed that you can get the correct results. So it's been a while that people couldn't understand why this is the case. It turns out it's because of the symmetry of this lattice. And so dipolar interaction, this long-range dipolar interaction is actually self-screened. So to some certain degrees, you can just use the short range, the nearest neighbor interaction, effective interaction to describe the physics. So this is what mathematically called the projective equivalence. But when the temperature is lowered, okay, something actually happens. So because there's still some residual dipolar interaction which is not included in this projective equivalence. So all this residual dipolar interaction will actually lift the degeneracy. And so for the dipolar spin ice, this is what's so-called an MDG state. It's kind of anti-ferromagnetic ordering state. And this is a state selected by the dipolar interaction from this massive degenerate manifold. So, but this state hasn't been observed. Okay, there's a recent experiment arguing that there's some signatures of this possible in ordering. Okay, so here is a specific heat measurement, and so in this experiment, it's a dysprosium titanate experiment, and they waited a very long time. I think a couple of weeks. So before they so they equilibrate very long, and so just make sure the systems go into the they are not trapped in the metastable state. So it shows sign that this Pauling entropy is partially recovered, but it's far from what the theory prediction, and so there's some argument that this might be impurity effect. So what we're interested in is actually we want to apply the magnetic field. And this is because of this one-on-one anisotropy, this material is actually very isotropic. Okay? So if you apply the field in the 100 direction and 111 direction and 110 direction, you get a very different saturation magnetization. And that's due to this 111 single ion anisotropy. So if you just take this nearest neighbor, sorry, there's some, I just erased that. But if you apply the material in the 100 field, okay, and there's a theoretical, you can induce a 3D cast line transition. So basically, you can start from a Coulomb phase, which is a spin ice phase, and go to an order phase, which is a fully polarized phase. And this transition can be understood as this proliferation of strings. Okay? So this is the order state, and you can consider the only way that you have a 111 field, a 100 field in this direction. So the only low-energy excitations will be just flipping a strings of spins from this boundary to this boundary. Okay? And so this transition actually is a proliferation of these strings. And interestingly, you can map this to a 2D Bosonic model. So this is a 3D classical model. You can consider this direction as an imaginary time direction. And then there's a Bosonic model. And this transition corresponds to a transition between the both condensate and the vacuum. And by tuning the field, it's basically just tuning the chemical potential of the Bosonic model. And so now we know that in the absence of the magnetic field, you get this Coulomb phase, which is a spin ice manifold. If you turn on the dipolar interaction, you get this order state. And if you apply a very strong 100 field, and you go into this fully polarized state. So the natural question to ask is, if I turn on the dipolar interaction, what's going to happen? Okay? And we know that for this system, at high temperature, it should be this Coulomb phase, and at low magnetic field, I should recover this order state in the dipolar spin ice, and at the very high field, I should get this. Okay, is there any surprises? Well, it turns out there is. Okay, so this is just a direct simulation of the dipolar spin ice in the presence of 100 field. In addition to this, so this is a fully polarized state, and this is this MDG state. This is non-magnetic. We find that there's a magnetization plateau with 1/2 magnetization in the middle. And I'm not really familiar with this pointer. So this is the state we found. So it's hard to see in this 3D picture. So if I do a mapping in the 100 direction, so the MDG state, okay, corresponds to some. So this is a fully polarized state. So all the spins pointing in the Z direction, okay? And this is MDG state, which is non-magnetic. So this half polarized state is basically composed of half of this fully polarized state and half of this MDG tetrahedrons, and they kind of stagger. And we observe a magnetization plateau, and at high temperature, which is the coolant phase, then there is no plateau. And at lower temperature, this plateau starts to build up. And so we can understand this by some level crossing of these states. So here is the MDG state in a field. So it's non-magnetic, so there's no field dependence. And this is the fully polarized state, and this is our state. Okay? And actually, we can take the simulation results and understand why this magnetization plateau exists. So this is a phase diagram that we get. So there's we plug in the dysprosium titanate parameters, and this field is tiny. And this order state has never been observed. But we believe that experimentally, if you go from here, fully polarized, and go through these transitions, things might be easier. Okay, so one interesting thing is that if you stare at this magnetization plateau, and it reminds of us as some kind of model. Okay, so here is the 2D Bosonic model with a nearest neighbor repulsion. Okay? And so there's a superfluid to solid transition, and so it seems that, and this normally is this melting transition normally is a first order, and we also have a first order transition, but because of this long range dipole interaction, we cannot really do the same mapping as what previously done in the Cas9 transition. So we don't know if this is a correct effective model, but I mean this similarity is really striking. As I mentioned, there's possible observation, and people have attributed to other order state, but it doesn't really match the numbers that we get. So maybe this, because the spin ice materials is very hard to equilibrate, maybe the system hasn't equilibrated yet. I don't know. So I'm going to the next topic. So this, we want to apply a field in the 1-1-1 direction, but slightly off the symmetry axis. So if you look at the 1-1-1 direction, this particle lattice basically you can think of it just Kagome layer, triangle layer, Kagome layer stacking. Okay? So if you apply large enough field, this the spin on the triangular layer is going to be pinned in the field direction. So the degrees of freedom are actually only on the Kagome layer. So you start from a spin ice phase, and you pin this the spin in the triangular lattice, in the triangular layer. Then the number of degeneracies is partially lifted, but there's still extensive number of degeneracy, and this corresponds to so-called this Kagome Ice. So if you have a downward triangle, then to satisfy the ice rule, because of this spin is already pointing up. So you have only pointing in. So you have only 2 out, 1 in configuration, but you still have some degeneracy. And if you further apply a stronger magnetic field in the 1-1-1 direction, you go to this saturated state. So all the spins pointing in the field direction. Okay. And this is the phase diagram, and this transition, okay, is basically equivalent to this liquid-gas transition. This is a first-order transition, and there's a latent heat. There's a critical point, okay? And experimentally, there's some observation that not only that it is Kagome ice and to this saturated phase, there's some intermediate phase that people have seen, okay? So it's this part, which is oscillating, and people didn't really know what's going on in that part of the phase diagram. So the interesting thing is that one can tilt this field away from the one-on-one direction. It depends on how you tilt, you can get different states. For example, if you do this positive tilt, so the way we define the angle is this way. Okay? So if you do a positive tilt, then energetically the system wants to flip all the spins flip the spins on the Kagome ice phase to enter this fully polarized state, so that the spins will be pointing along the field direction. So this again is a cast iron transition. But if you tilt the field in the other direction, there's still degrees of freedom, okay, which is not exactly in order, so you still have some residual degeneracy. But interestingly, experimentally, they see something which doesn't correspond to this degeneracy, and what they see is that near this critical point, they find some order state or critical scattering. So indication this is going to it's very close to a transition. Okay? And they did a simulation without this dipolar interaction, and they can produce all the features away from this critical point, but near a critical point, this very naive model cannot really do this. Okay? So by including so we argue that this ordering is actually again induced by this residual dipolar interaction. So we did a simulation, and we can see some spot at the exactly the same. So it's not really the critical scattering as seen in experiment. Okay, I will show you later, but we can see some kind of ordering at this exactly the same wave vector, and this is picked by the dipolar interaction, this residual dipolar interaction. Running out of time, so just go quickly. So we check if this is order state, and we do see that if we are going through this transition, we do see this recovery of all the residual entropy. So this is a unique ground state. So it turns out we look at the configuration, and this is what people called it the Q=X state. So it's hard to see from here, but you can see that if you look at these chains, so these are red spins and this yellow spins, they are actually anti-Fermi orders. So basically, the system going from the Kagome ice state goes through a first order transition by ordering these chains. Okay. So without dipolar interaction, this chain, there's no the configuration of these chains. Their energy are equivalent, so there's no ordering of this chain. But if you turn on the dipolar interaction, then the system will pick up this kind of ordering, and you can, because of this dipolar interaction in this plane, they want to be anti-ferromagnetic aligned. Okay? So this is basically, we understood this transition as anti-Fermi ordering of this this chain, and this chain is what people call the beta chain. So with this, we're able to reproduce this phase diagram. So basically, what's plotted here is intensity from a neutron scattering, and we can clearly identify some very similar structures from theory and experiment. The only difference is that what we see is an ordered state, but what experimentally see is actually a critical scattering. One interesting thing is that while we're writing this paper, we saw this paper on the archive, and people re-examined their data, and they realized that they actually just, in the experiments, there might be some tilting. Okay? They don't know how much they tilted, but there's some tilting, and so there's a intermediate state. And so this looks very similar to what we get from the simulation. Okay, so let me conclude. So in the 1,0, if you put a dipole spin ice in a 1,0,0 field, we found that a new phase, which is called a half-polarized phase, which is stabilized by this dipole interaction. And it shows very strong similarity with the phase diagram in 2D Bose-Haber model. But how these two physics are mapped, we still don't know. And we found that in the tilted field physics, it's actually this that what people observe in the experiments may be indicative of indication of antivariant ordering transition from a Kagome ice to this beta chain ordering state, which is called Q equal to X state. What we see in the simulation is the first order transition, but neutron shows a critical scattering. Is it possible there's some other effects in the experiments which is not taken into account in our simple-minded model? One possibility is that because this tilted field is so hard to control, so there's possible that there's another direction that the experimentalist can tilt the field accidentally, and so by tuning this, there might be some multi-critical point in some other field direction, and this is what we're still trying to figure out. And the thing is that there's no symmetry argument you can do says this must be a first order transition. Okay, so this is still some puzzle. And what we're looking at currently is that we want to understand the dynamics. So if you can generate monopoles in these systems, how they move, what kind of, can we learn something can we learn something, because in the simulation we see very slow dynamics, but in the experiment, that doesn't seem to be a case. So we're trying to understand what causes the difference between this simulation dynamics and the real dynamics. So another thing we're looking at is that this dipolar condensed spin ice, are there similar phases that you can find? Okay, so I'm just going to pull up this. So this is a simulation of a quantum spin, dipolar quantum spin ice by tuning J2. So here is the quantum phase diagram. Here's the classical phase diagram. And aside from a small phase, it seems that there's a very similar phase diagram that one can construct. So we are actually now doing the same, playing the same game, but in the quantum spin ice. And we do some signature of this half-polarized state. So that's my talk. Thank you.
Some time for questions. So I can ask one. So where is the half-polarized state on?
No, that's.
Which is it related to one of the phases on this diagram?
No. So we are actually, so this is without any magnetic field. This phase diagram is without any, this is published paper. So we are speaking along this line that we see this order phase in the classical simulation, and this study tells us that seems to be a one-to-one corresponds between a classical system and the quantum system. I mean the quantum phases, and so maybe there's an interesting quantum phase also in the quantum spin ice. That's what we're running.
So can you argue that the half-polarized phase will survive quantum fluctuations?
I have no good arguments if it should live or die. I don't know, but it seems from our initial study, it seems that it should live. There's some signature of that.
Other questions? Right, so let's thank the speaker once again.